statement regarding circuit breakers being constructed so that they will not open under the magnetic forces resulting from short-circuit current is crucial for understanding how these protective devices function. It seems counterintuitive at first because the main purpose of a circuit breaker is to open a circuit when there is an overcurrent condition, such as a short circuit. However, the key lies in the magnitude and duration of the forces involved during a short circuit. A circuit breaker is designed to protect an electrical circuit from damage caused by an overcurrent or short circuit. It does this by interrupting the flow of current when it exceeds a predetermined level. Circuit breakers have two main mechanisms for tripping. Firstly, thermal tripping relies on a bimetallic strip that heats up and bends when subjected to overcurrent. This bending action triggers the release mechanism, opening the breaker. Thermal tripping is slower and designed to protect against sustained overloads. Secondly, magnetic tripping is much faster and responds to the intense magnetic field generated by a short circuit. This magnetic field pulls on a plunger or armature, which instantly trips the breaker. When a short circuit occurs, the current rises extremely rapidly to very high levels. This rapid increase in current creates a correspondingly strong magnetic field around the conductors and within the circuit breaker itself. This magnetic field exerts a force on the breaker's internal components, including the contacts and the tripping mechanism. The magnetic forces generated during a short circuit are substantial, and if the circuit breaker were not designed to withstand them, the forces could cause the breaker to open prematurely or even be damaged. If the breaker opens prematurely due to these magnetic forces and not due to the intentional tripping mechanism, several problems can occur. Firstly, nuisance tripping. A circuit breaker might open unnecessarily, interrupting power to the circuit even if the fault current has not reached a dangerous level or the breaker's intended tripping point. This can cause downtime and inconvenience. Secondly, contact damage. The contacts of the circuit breaker are designed to withstand the normal arcing that occurs when the breaker opens under load. However, if the breaker is forced open by magnetic forces, the contacts may not separate cleanly, leading to excessive arcing and damage. Thirdly, failure to interrupt the fault. The primary purpose of the circuit breaker is to interrupt the fault current quickly and safely. If the breaker is damaged or opens prematurely, it may not be able to interrupt the current effectively, leading to further damage to the electrical system and potentially creating a fire hazard. Therefore, circuit breakers are designed with robust mechanisms and materials to withstand the magnetic forces generated during a short circuit. The components are braced and supported to prevent them from moving or deforming under these forces. The tripping mechanism is designed to be immune to these forces until the current reaches a level that requires the breaker to trip. The statement in question emphasizes that the circuit breaker must be constructed in such a way that it will not open solely due to the magnetic forces resulting from a short circuit current. It must only open when the intentional tripping mechanism is activated by the overcurrent condition. This is achieved through careful design and engineering of the breaker's internal component. The circuit breaker's ability to remain closed despite the magnetic forces until the appropriate overcurrent level is reached ensures that it functions correctly and protects the electrical system from damage. The design of a circuit breaker involves considering several key factors. Firstly, the interrupting rating. This is the maximum short circuit current that the breaker can safely interrupt without being damaged or failing. Breakers are tested to ensure they can handle these high currents. Secondly, the voltage rating. This is the maximum voltage the breaker can be used in a circuit. Using a breaker with a lower voltage rating than the circuit voltage can be dangerous. Thirdly, the ampere rating. This is the continuous current the breaker can carry without tripping. It should be matched to the circuit's load. Fourthly, the tripping curve. This is the time current characteristic that defines how quickly the breaker will trip at different levels of overcurrent. It is chosen based on the application and the types of loads being protected. Fifthly, the construction materials. The breaker must be made of materials that can withstand the heat, magnetic forces, and mechanical stresses of normal operation and fault conditions. The calibration and testing of a circuit breaker are essential to ensure it operates correctly. Calibration involves setting the tripping point of the breaker to the correct level. Testing involves subjecting the breaker to various overcurrent and short-circuit conditions to verify its performance. Some common types of circuit breakers include firstly miniature circuit breakers, or MCBs. These are used in residential and light commercial applications. Secondly, molded case circuit breakers, or MCCBs. These are used in higher current applications and can have adjustable trip settings. Thirdly, air circuit breakers, or ACBs. These are used in main switchboards and substations for high current protection. Fourthly, ground fault circuit interrupters, or GFCIs. These protect against ground faults, which can be very dangerous. GFCIs are commonly used in bathrooms and kitchens. Regular inspection and maintenance of circuit breakers are essential to ensure they remain in good working order. This includes checking for signs of damage, testing the tripping mechanism, and ensuring the connections are tight. A damaged or malfunctioning circuit breaker should be replaced immediately. In summary, the statement about circuit breakers not opening under magnetic forces from short-circuit current means the breaker must be designed to withstand these forces and only open when the intended tripping mechanism is activated by an overcurrent. This ensures the breaker functions correctly and protects the electrical system from damage. Understanding the design and operation of circuit breakers is essential for electrical safety. Circuit breakers are a critical component of any electrical system and play a vital role in protecting people and property from electrical hazards. They are designed to interrupt the flow of current when a fault occurs, preventing damage to equipment and reducing the risk of fire or electric shock. The NEC, or National Electrical Code, provides detailed requirements for the selection, installation, and maintenance of circuit breakers. Adhering to these requirements is essential for ensuring the safety and reliability of electrical systems. Some of the relevant NEC articles related to circuit breakers include firstly Article 240, which covers overcurrent protection in general, including circuit breakers and fuses. Secondly, Article 408, which covers switchboards and panel boards, which are often the location of circuit breakers. Thirdly, Article 430, which covers motor circuits and motor circuit protection, including the use of circuit breakers. Fourthly, Article 450, which covers transformers and transformer protection, including the use of circuit breakers. These articles provide specific requirements for the ampere rating, interrupting rating, and other characteristics of circuit breakers, as well as requirements for their installation and maintenance. The interrupting rating of a circuit breaker is a critical parameter that must be carefully considered. The interrupting rating is the maximum short-circuit current that the breaker can safely interrupt without being damaged or failing. The interrupting rating must be greater than the available fault current at the point of installation. The available fault current is the maximum current that could flow in a circuit during a short circuit. It depends on the source voltage, the impedance of the circuit, and the characteristics of the electrical system. Calculating the available fault current requires careful analysis and may involve the use of specialized software or equipment. Failure to select a circuit breaker with an adequate interrupting rating can have serious consequences. If the available fault current exceeds the breaker's interrupting rating, the breaker may fail to interrupt the current, leading to damage to equipment, fire, or electric shock. In addition to the interrupting rating, the ampere rating of a circuit breaker is also an important consideration. The ampere rating is the continuous current that the breaker can carry without tripping. The ampere rating must be matched to the load being protected. If the ampere rating is too low, the breaker may trip unnecessarily, interrupting power to the circuit. If the ampere rating is too high, the breaker may not trip quickly enough to protect the circuit from damage. The selection of a circuit breaker also depends on the type of load being protected. Different types of loads have different current characteristics and require different types of circuit breakers. For example, motor circuits often require circuit breakers with inverse time characteristics, which means they trip more quickly at higher levels of overcurrent. This is to protect the motor from damage caused by sustained overloads. Ground fault circuit interrupters, or GFCIs, are specialized circuit breakers that protect against ground faults. A ground fault occurs when current flows from a live conductor to ground. This can happen if a wire is damaged or if a person comes into contact with a live conductor. GFCIs are designed to detect very small ground fault currents and trip quickly, preventing electric shock. GFCIs are required in many locations such as bathrooms, kitchens, and outdoor areas. The installation of circuit breakers must be done in accordance with the NEC and the manufacturer's instructions. Circuit breakers must be properly mounted and connected to the electrical system. The connections must be tight and secure to prevent overheating and arcing. Circuit breakers must also be properly labeled to identify the circuits they protect. Regular maintenance of circuit breakers is essential to ensure they remain in good working order. This includes inspecting the breakers for signs of damage such as cracks or discoloration. It also includes testing the tripping mechanism to ensure it is functioning properly. Damaged or malfunctioning circuit breakers should be replaced immediately. Testing the tripping mechanism of a circuit breaker can be done using a circuit breaker tester. This device applies a controlled amount of current to the breaker and measures the time it takes to trip. The results of the test can be compared to the manufacturer's specifications to determine if the breaker is functioning properly. Circuit breakers are an essential component of any electrical system and play a vital role in protecting people and property from electrical hazards. Understanding the design, operation, and maintenance of circuit breakers is essential for electrical safety. By following the requirements of the NEC and the manufacturer's instructions, you can ensure that your electrical system is properly protected.